12th tunneling. Welcome everyone to the 12th tunneling in QFT seminar. As usual, this will be recorded and put up on YouTube. This is our first seminar of 2025. And today we have Andrey Shkerin from Perimeter Institute. He was previously a postdoc at Minnesota University and before that did his PhD at École Polytechnique in Lausanne. He's worked on tunneling over many years, from electroweak stability and the metastability during inflation, sphalerons, some other things on the hierarchy problem and non-topological solitons, and more recently on black hole-induced tunneling, and the topic of today, which is thermal tunneling. Yeah, I'm very interested to hear how it goes. Next month, we have Matthias Carosi on the 20th of February. So hope to see you all there for that too. But Andrey, please take it away.
Okay, thank you very much for inviting me to give a talk at this seminar. So I will talk about thermal false vacuum decay and how it is not what it actually seems. And this is a ongoing work essentially. This talk will be based mostly on these two papers that are available already, and this has been done in collaboration with Dalila Pirvu, who was a PhD student at PI, and Sergei Siberyakov, who is a faculty also at PI. So vacuum decay, essentially, it is a first order phase transition. So let me remind you briefly why it is so interesting and important to study first order phase transitions. And the theory of decay of a metastable state of false vacuum covers a broad range of phenomena in different branches of physics. So it describes various phenomena such as boiling water or boiling vacuum of the standard model of particle physics. And it plays an important role in various branches of physics, from quantum matter, condensed matter, to particle physics and cosmology. And naturally, studies of decay of metastable state have a very long history, more than a century-long history. And only a small part of it actually belongs to the high energy physics, but that is this part that I will mostly focus on. To clarify, we will consider thermal first-order phase transitions, which means that the initial state of the system, the metastable state, is in local thermal equilibrium around the metastable state, which means that one can assign a temperature to the state. And the key observables of any theory describing first-order phase transitions is a rate of decay, that is a probability of the phase transition happening per unit time, per unit volume, the size of the critical droplet of new phase that is stable and not stable, but which starts expanding rather than contracting. So this, I would say, the key observables, and any theory must predict them. And let me give you a brief review of the historical developments in the theory, because this is rather interesting, actually. So it all can be traced back to their original works by Gibbs in the 19th century, who in the paper dedicated to studying phase transitions in heterogeneous substances, so the substances containing two phases. And apparently he was the first to discuss the critical bubble and calculate its energy, its size, using what we would call now thin wall approximation. So separated the volume of the contribution to the energy coming from the volume of the new phase, balanced by the tension of the wall separating the two phases. So that was very nice. Later, one can mention the works by Wigner, who was a prominent chemist, actually. And in his works already, one can see a familiar vocabulary. So he discusses cell point of the free energy, separating the metastable and stable phases, negative mode, that is which describes instability of the cell point, zero modes, and many other things. And this is what one can call transition state method, which is a standard benchmark theory, essentially, in physical chemistry, which studies reaction rates in molecules or substances. Then Kramers derived the rate for the Brownian motion of a classical particle to cross a barrier. And the classical particle was coupled to some external heat bus, and he studied how it moves through the barrier, different viscosity. But this was still a mechanical treatment. So Langer, in 1969, introduced classical statistical theory metastability, which actually comes quite close to field theory already, because here it's a system of many degrees of freedom, so not that different from the field theory, which is coupled to some external heat bus, so its motion is governed by not only internal dynamics of the system, but also by stochastic terms like dissipation and noise, which come from coupling the system to some external heat bus or thermostat. But that was a classical treatment. Affleck considered the problem of the escape from a metastable state of a quantum mechanical particle, so that was a quantum system. But only 1 degree of freedom, so only one particle. But that was generalized finally by Linde, who gave like the general theory, or maybe the method, how to calculate the decay of false vacuum at finite temperature, and both in the quantum regime, where tunneling is important, and in the classical regime, where thermal activation, thermal jumps over the potential barrier is important. So there was a similar line of development in other branches, such as condensed matter or soft condensed matter or physical chemistry, but I know much less about these developments. But one common thing about these developments is that we always have some benchmark theory which gives us certain predictions about key observables, such as decay rate or the shape of the critical bubble, which we need to test in experiments or maybe in numerical simulations. And in the case of high energy physics, we can call the theory the Euclidean theory, or the equilibrium, or the thermal field theory. And one more common feature is that these theories do not always give the correct predictions. So just a little bit motivation to study vacuum decay, but this time I'm going to focus on particle physics and cosmology. And here there is a lot of motivation. One can mention first order phase transitions in cosmology that could happen in the early universe, predicted by many extensions of the standard model. And why is this interesting phenomenologically? Why? Because, for example, nucleation, propagation, and collision of bubbles may generate gravitational waves. And this is actually motivation to improve existing and build new gravitational waves detectors that hopefully will be sensitive to this gravitational wave signal, which is a signal of new physics, essentially. And this is also motivation from the theoretical point of view to improve our theoretical calculations of the gravitational wave signal from such cosmological phase transitions. Next, one can also mention generation of baryon asymmetry of the universe, which is also not fully resolved. We don't have like a unique theory predicting the abundance of baryons or antibaryons. And here the idea is that expanding bubbles moving through cosmic plasma can generate such an asymmetry. So again, it is important to pay attention to possible cosmological phase transition in this respect. One can also mention metastability of the standard model vacuum, because according to the measured values of the parameters of the standard model, our fundamental vacuum, the Higgs vacuum, may itself be metastable. And while it is true that in the present day universe, low density, low temperature, the decay probability is very small, so we are safe. However, this may not be so in extreme environments, such as happening around black holes, or maybe in early epochs in the past, such as, for example, during inflation. So again, there is strong motivation to refine both theoretical predictions and to look for possible observational signatures of such vacuum decay. And last but not least, one can do experimental tests of nucleation theory in relativistic. That is important, that these experimental tests of relativistic nucleation theory, and there have been proposals to make such tests using cold atom systems. And the first result, the first successful experiment has been recently reported. So again, we need to know, or we need to be able to make accurate theoretical predictions so that we can go and test them in experiment. Okay, so let me now give you the main observable, the main prediction of the theory, which I will talk about in this talk, and that is the decay rate. So I will focus on the decay rate. And in the regime when the decay is exponentially suppressed, can be expressed by this relation. And this B term is, we can call it exponential suppression. And this is a sort of leading order prediction or leading order calculation in the semi-classical approximation. And it gives the main prediction about the decay rate, because it tells us that the decay rate is exponentially suppressed. But there is also the prefactor, the dimensional prefactor. And it is important to be able to compute this prefactor as well. And this is next to the leading order computation in the semi-classical approximation. So the key points about this computation is that the exponential suppression is computed using the stationary point of free energy, or the classical solution of equations of motion, and that bounds. And the prefactor is typically evaluated by, it involves a determinant of small fluctuations computed around this bound solution. And in principle, both the exponential suppression and the prefactor are calculable in the given framework. For example, in the framework of thermal field theory, so it is very challenging to do it in practice. So if the typical picture of how the exponential suppression behaves as a function of temperature, different temperature, it looks like that. So at zero temperature, we have some vacuum suppression. And in this regime, the decay is possible only via quantum tunneling of the system through the barrier. So here is a schematic plot of, say, the free energy of the system. And here I choose one of the coordinates to be like the reaction coordinates. And the tunneling happens along this particular direction in the free energy. So when we start increasing the temperature, still we have tunneling as a main channel of decay. But now this is a thermally assisted tunneling, since now we have thermodynamic fluctuations. So now the metastable state is populated according to the Gibbs distribution. And so tunneling is possible not only from the ground state, but from the excited states of the system as well. And then it actually happens from some energy level, which can be found again in the semi-classical approximation. Typically, there is some critical temperature above which decay becomes purely classical. So above this temperature, tunneling is not important anymore, and decays happen via classical thermal jumps over the barrier. So here, thermodynamic fluctuations are so strong that they can just throw the system over the barrier classically. And in that case, we actually get the usual Boltzmann suppression, as we should. So this coefficient B equals the energy of the barrier, the energy of the critical bubble divided by the temperature, which is a Boltzmann suppression. Actually, it's interesting that it is not really fully understood yet what is the nature of this transition point between the two regimes, the quantum regime and the classical regime, how the system really behaves near this transition point. For example, how the exponential suppression behaves. Is this curve always smooth, or it can be only continuous? That's one question that one may ask, and the answer happens to be model dependent. So that really depends on the system at hand. It is even less certain what one can say about the prefactor around this point, because the prefactor may well be discontinuous, because on the other sides from this point, we essentially have different saddle points. So one is a saddle point corresponding to the bounds describing tunneling, and another is a saddle point describing the critical bubble. So there is still, even in this typical plot, typical picture of vacuum decay, there is still a lot to be studied. But from now on, I will focus on this part of the plot describing thermal activation. So I will focus on classical transitions only. So we assume that the temperature of the system is high enough so that decays happen in the classical regime, but it is not too high, and the decays are still exponentially suppressed. And then, as I discussed, it is just the Boltzmann suppression. In this case, we can use standard thermal or equilibrium theory to calculate the decay rate. And one can write some fairly general formula for the decay rate. So here, F is the free energy of the system computed around the false vacuum. V is the volume, T is the temperature, and omega minus is a growth rate along the unstable direction of the critical bubble. So 1 over omega minus is the characteristic time of nucleation. So it is a characteristic time of the growth of the critical bubble. And that is actually a very important dynamical time scale that will play an important role later. So this is what the Euclidean theory tells us. The Euclidean theory cannot tell us everything about the phase transition. For example, it cannot tell us about the real-time dynamics of the phase transition. It cannot tell us what exactly happens in the metastable state, how exactly these thermodynamic fluctuations propagate and build and create this critical bubble. And to study such real-time dynamics, and also to test the main prediction of the Euclidean theory using some independent method. So here one can use real-time classical lattice simulations. Indeed, in the classical regime, if occupation number of all relevant for the decay degrees of freedom are big, then we can just model the theory classically on a classical lattice with appropriate initial conditions. We can run the numerical simulation and just see what happens. So this is a numerical experiment. And we can measure the observables, including the decay rate, and compare them with the prediction of the Euclidean theory. So that was our goal initially. And of course, such simulations have been performed in the past for various purposes. And this is a selection of works in this direction. So one can mention the works by Grigoriev, Rubakov, Shapashnikov back in 80s, 90s, who did real-time simulation in abelian Higgs model, for example. They wanted to study Sphaleron transitions, and they wanted to measure the rate of Sphaleron transitions and compare with the Euclidean prediction. But they also studied, for example, kink production and annihilation. And in doing so, they used the Hamiltonian dynamics of the fields. I will discuss that later. One can also mention some works by Alford, Feldman, Gleiser, and others who studied vacuum decay, among other things. But they used Langevin dynamics instead. So the system was implicitly coupled. There was an implicit heat bus, and they used Langevin dynamics to model the coupling of the system to the heat bus. I will discuss that later as well. Finally, one can also mention works by Gould, Moore, Rummukainen, and others who were also interested in studying vacuum decay. But in the regime, when it is so much suppressed, the exponential suppression is so big, there is no chance to really see, to model it directly on a lattice. So they used a more complicated technique of multi-canonical sampling, which actually preselects configurations which are already sufficiently close to the critical bubble, and then the real-time evolution allows to reconstruct or to measure the dynamical prefactor, for example, in the decay rate. So what did we do in our work? We took the simplest, set up the simplest theory, which is a scalar field theory in 1 + 1 dimension with quadratic self-interaction. So the potential of the theory behaves this way. We have the false vacuum around phi equals 0. We have the barrier, and then we have the true vacuum region on the other side of from the barrier. And the true vacuum is really a runaway. Phi goes to plus minus infinity, but that is not really important. So we take the theory and we discretize it on a spatial lattice. And this gives us the following classical system described by this Hamiltonian. And essentially, we should study the dynamics of the system, the evolution of the system. So the system is evolved according to the Hamiltonian equations of motion. I write them here. And okay, so we know the equations of motion, and we can now take a suite of simulations, but we must also prepare the initial state properly. We must prepare the initial state, which corresponds to thermal equilibrium around the false vacuum, phi equals 0. And this is a subtle point because we must be very careful about preparing the initial state, because the decay rate is exponentially sensitive to the state. So if we are slightly off equilibrium, for example, if the temperature is not the temperature that we want, then we may get a drastically different answer for the decay rate, and we want to make an accurate measurement of the decay rate, including both the exponential suppression and the prefactor. So we must be careful about preparing the initial state. Well, hopefully, in this case, for this simple theory, we know analytically, more or less, what the initial state is, because in equilibrium, in 1 + 1, it is almost the Rayleigh-Jeans spectrum regularized by finite lattice spacing, and we can set it up explicitly. Strictly speaking, the Rayleigh-Jeans spectrum describes equilibrium in a free theory. So we must account for, at least for the leading effects of self-interaction in the theory. It turns out that in this case, the leading effect of self-interaction is a thermal correction to the mass, as I write here. So in the weak coupling regime, where this parameter, which is the only parameter in the model after we rescale the variables properly, so this parameter must be much smaller than 1. It controls both weak coupling and the expansion, the weak coupling expansion, and the exponential suppression of the decay. So if this parameter is much smaller than 1, then we can compute the thermal correction to the mass in perturbation theory, and this is a leading correction. And even if this parameter is 0.1, as we typically take in our simulation, then this correction is about 15%. And that turns out to be important. So we must really take into account when preparing our initial state. This 15% correction is important. We also tried different methods to prepare the initial state, which are not to set up the state explicitly, but rather to use some, for example, Hamiltonian Monte Carlo, which guarantees that the system approach its true equilibrium state, even if we don't know it exactly. Or we can even use the Langevin evolution, the short period of the Langevin evolution, when we couple the system to some external heat bus and let it evolve for a while until we believe that thermal equilibrium is established, after which we decouple it from thermal bus and let it evolve on its own. So we tried these different methods, and apparently they all give the same results. So the results of our simulations agree with each other. So that is nice. Yeah, so this is a schematic picture of what we do in our simulations. So we prepare the initial state, then we let the system evolve according to these Hamiltonian equations of motion, and it takes it a long time to evolve in this false vacuum region. This evolution is presumably ergodic, until finally it crosses the bottleneck, which is a critical bubble, and runs away, decays. After which we stop our simulation and start again. Of course, in most of the simulation, the decay never happens, so we also have some time constraint. Okay, so let me now describe how we actually measure the decay rate and compare it with the theory. So in this theory, one more advantage of this simple toy model is that we can actually compute analytically both the exponential suppression and the prefactor. So we have the exact formula for the decay rate, which is given here, where m is the mass of the field, t is the temperature, and E is the energy of the barrier. That is, it is the critical bubble energy. And to measure the decay rate in numerical simulations, what we really measure is the survival probability. So we measure how many configurations or how many simulations have not yet decayed by time t as a function of t. And for decays obeying the exponential distribution, the survival probability apparently follows this law. So if you take the log of it, we should get this simple linear dependence of the log of the survival probability, where constant term accounts for possible early time transients, which we exclude, and the rest is just the linear slope. So the Euclidean theory, if you look at this plot, the log of survival probability as a function of time, the Euclidean theory predicts the straight line with a certain slope. And then we just go ahead and measure this in simulations, and this is what we get. The blue line is what we get from simulations. So apparently there is a big discrepancy, and the two key points is first, the decay rate found in simulations happens to be smaller than the Euclidean prediction. Well, here it is, we see it is smaller by almost an order of magnitude or more. But not only that, it actually turns out to be time dependent in our simulation. So this time gets even smaller. So we have to understand what happens. And to understand what happens, let's look a bit more carefully at what do we mean when we say thermal, when we say that the system evolves in thermal equilibrium, right? Remember that we prepare the system in thermal equilibrium, but after that, we let it evolve on its own, right? So the system in this particular set of simulations evolves according to its own Hamiltonian dynamics. So in this case, what we really understand when we say, what we really mean when we say thermal evolution, we mean the following, that in this system, we can select a certain subsystem which consists of the Fourier modes of the field which are actually relevant for the decay. And these are the long modes. These are the modes with wavelengths of the order of the inverse mass of the field, because that is the size of the critical bubble. So these modes, the dynamics of these modes is important. That is what determines the decay. The rest of the system, on the other hand, which contains short Fourier modes of the field, all modes up to the cutoff, which is set by the lattice spacing, they do not participate directly in building this critical bubble. Instead, they provide the background for the long modes. So the short modes, they play the role of the thermostat. The big thermostat, which is supposed to keep our small but still macroscopic system in thermal equilibrium. So the big thermostat has a certain temperature, and the system is also supposed to have the same temperature. However, the implicit assumption here in this picture is that the coupling between the system and thermostat is efficient enough so that the thermalization time is small enough, the relaxation time, smaller than any other time scale which is relevant for our problem. But it turns out that in this particular system, the thermalization is not efficient at all. It is easy to estimate the relevant time scale at which the long modes talk to the short modes, and for modes with wavelengths of the order of the bubble size, the thermalization scale is proportional to the inverse force power of the small parameter. Remember, this parameter is a small semi-classical parameter which controls the weak coupling and which controls the exponential decay. So it has to be small. So this thermalization time happens to be much, much bigger than, well, the characteristic scale of nucleation. And in our simulations, it happens to be even bigger than the characteristic decay time, which is inversely proportional to the decay rate. So the decay time is exponentially long. Nevertheless, in our simulations, the thermalization time happens to be even longer than the decay time. Okay, this is certainly not the hierarchy which you would naturally expect, but this is what might actually happen. And when this happens, this leads to the interesting effect, which we call classical Zeno effect. So what it means is the following. At such an efficient thermalization, at time scales of the order of the decay time, so time scales which we are interested in, the relevant subsystem is essentially decoupled from the thermostat, so they do not talk to each other. So if the system has some temperature, which may not be the same as the temperature of thermostat because we prepare the initial state in thermal equilibrium, but there are fluctuations. There are always statistical fluctuations. So the effective temperature of the system need not be the same as the temperature of the thermostat. It will be the same on average when we take the ensemble average. But in any given simulation, it is not the same. But the important point is that the temperature is essentially preserved during the simulation because there is no way the thermostat, the coupling to the thermostat is not sufficient to thermalize the system on a relevant time scale. But that means that simulations which have a higher initial effective temperature due to some statistical fluctuations, they preserve this high effective temperature during the simulation. But this effective temperature is what is most important for the decays, right? Because the decays happen here. So they have more chance to decay because they have more power. The simulation have more power stored in the long modes. So on average, such simulations decay faster, of course. But that means that when we study simulations, when we study the ensemble of simulations that are survived by a certain time t, the statistical properties of these surviving configurations of the remaining ensemble, they change with time. So the decays introduce bias into the ensemble. And the change is that the long modes cool down. So as time goes by, in the surviving simulations, in the surviving ensemble, simulations are going to have less and less temperature, less and less power stored in the long modes. So we can actually see this numerically because it is easy to measure the effective temperature of the simulations which survive by time t and plot it as a function of t, as a function of time. And then we indeed see that this is what really happens. So as time passes, the modes with long wavelengths, with small momenta, they cool down visibly. They cool down by a few percent during the simulation time. And remember, the decay rate is exponentially sensitive to the temperature. Well, in this case, it is effective temperature. So no surprising that the decay rate goes down as well. So this is a very peculiar situation when decay happens to be a non-Markovian process in this regime, right? Which is kind of curious. So the longer we observe the system, the less chance it has to decay in the future. So this resembles a Zeno effect, and but in this case, it has nothing to do with quantum mechanics. So this is a purely classical effect, and essentially this is just the statistical effects. So it is about statistics of rare events, essentially. Okay, we understand the reason for the time dependence of the decay rate, but this is not what we want to measure, because what we want to measure is the original decay rate, right? The decay rate in the original unbiased ensemble, because it is this decay rate which the Euclidean theory predicts. So to find this unbiased rate, we do some procedure. We measure the slope of the survival probability as a function of time, and then we extrapolate it to zero and to zero time. And this way we recover the decay rate of the original system. And here we have another surprise. So recall that the decay rate is given by this formula. A is a prefactor and E is the energy of the critical bubble. So we can parameterize this temperature dependence using this formula. So B is a critical bubble energy measured in simulations, and A is a prefactor, and we separated the temperature dependence from the prefactor. We account for it independently because this is a universal temperature dependence which comes from the zero mode of the prefactor. So we just measure the unbiased decay rate at different temperatures, and we fit it with this formula, which has two fitting parameters. And this way we find the energy and the prefactor. So the left plot shows you the measurement of the energy of the critical bubble. And here we have a perfect agreement with the Euclidean theory. So the agreement is within error bars, and error bars are very small. In our simulations, we have large statistics, and the error bars are less than 2%. And we agree perfectly well with the Euclidean theory. However, when we measure the prefactor, we get the value which is still off the prediction, and it is actually significantly smaller. So the measured prefactor is still smaller by almost an order of magnitude from the Euclidean prediction. Okay, and that was a second surprise and the second challenge. Now we have to understand the reason for this discrepancy. Now, immediately, the suspicion is, again, this has something to do with a small thermalization in the system. Thermalization that somehow is so inefficient that it fails to keep the system or the relevant part of the system in thermal equilibrium during the bubble nucleation process. And this is what we wanted to check next. But to check that, we need actually an additional handle, because so far in this system, we do not have a control over the efficiency of thermalization. We cannot really control the thermalization time in our system because the system has just one parameter, the temperature, and all other parameters are expressed via this single parameter, so we cannot really disentangle the nucleation time and the thermalization time and the decay time. So if you want to disentangle this, we do the following trick. We take our system and instead of coupling it to the inefficient heat bus, which is part of the same system, we introduce an additional heat bus, a big external heat bus, which is coupled to the relevant subsystem. And we would like to control the strength of this coupling. We would like to control the thermalization time. So how do we do this in practice? In practice, we do this by promoting the Hamiltonian equations of motion to the Langevin equations. So Langevin equations describe the system which is coupled to some external degrees of freedom, to some environment, which we do not treat explicitly. So we do not evolve the degrees of freedom of this environment, and we actually don't care about the particular structure of this heat bus. The only thing we care about is how strongly the system is coupled to the heat bus. And the strength of this coupling is controlled by the dissipation coefficient. So here you see in the Langevin equation, we have two additional terms. The first is a linear damping term, and the second is a noise term. Xi here is a noise variable, and it is a white noise. So these variables are independent Gaussian variables with zero mean and variance given by this expression. And the coefficient here, sigma, is related to the damping coefficient by the fluctuation dissipation theorem. So with this relation, the system evolved according to the Langevin equation is guaranteed to remain in thermal equilibrium And the characteristic time scale of equilibration is now set not by the internal dynamics of the system, but by the strength of its coupling to the thermostat, but that is a damping coefficient. So the thermalization time is simply inversely proportional to the damping coefficient. Okay, so we repeated our simulations using these Langevin equations. And this is the main result of the simulations. So let me explain a bit what this means. So first of all, we observed that when the damping coefficient is bigger than the inverse decay time, which is gamma times L, the size of the system, then there is no more Zeno effect. So the decay rate becomes time independent. And this is what we expect, right? So now thermalization happens faster than decays, and the coupling to the thermostat is now efficient enough to maintain the system in equilibrium, to maintain this ensemble, the statistical properties of the ensemble the same, unchanged during the simulation time. So that's one good news. Another good news is that when the damping coefficient increases, we see that the decay rate decreases. Sorry, when the damping coefficient increases, we see that the decay rate increases as well. And what is plotted here is again the ratio of the measured prefactor to the prediction of the Euclidean theory. And we see that we are getting really close to the Euclidean prefactor when the damping coefficient reaches 10 to minus 1 in units of the mass of the field. So what happens afterwards is that decays become suppressed again. The decay rate goes down again. But the reason for that is that if we keep increasing eta, eventually the system enters the regime of overdump. It becomes overdump, the evolution of the relevant modes. And so decays become suppressed again. We inhibit the evolution of the system across the barrier. And in this regime, we actually have a good theory, which is essentially Langer's classical statistical theory, that predicts how the decay rate behaves as a function of the damping coefficient in this regime of overdamping. And we actually reproduce in our simulations the correct asymptotics. So we reproduce the correct dependence on the damping coefficient. So here the decay rate must be inversely proportional to the damping coefficient, and that is what we see from simulations. We still do not have a perfect agreement for the decay rate, but this is due to the fact that, this is due to the fact that we deal with a field theory. So we do not have, our system is not exactly described by Langer's theory, but we are getting close to it. And another important observation is that we seem to be getting closer to this upper bound, which is the Euclidean decay rate, when we decrease the temperature of the system. We cannot really decrease it too much because the decay rates becomes very much suppressed, and then we just have no computational power to really perform evolution of the system for such a long time. But nevertheless, we see that when we decrease the temperature even a little bit, the decay rate increases. So these results lead us to the following conjecture about the thermalization time. The thermalization condition, which must be satisfied for the Euclidean theory to give the correct prediction about the decay rate. And I write this condition here. So thermalization time must be smaller than this time scale. So the time scale contains, so it is a product of two factors. The first factor here is the inverse growth rate of the critical bubble. And as we discussed, this is just a nucleation time. So it tells you how fast the system passes through the bottleneck, how fast the critical bubble grows. So this is a nucleation time scale. And then it is actually very natural to expect that if you want to maintain the system in perfect local thermal equilibrium at all stages of the nucleation process, then you would expect the relation like that. The thermalization time must not be bigger than the characteristic nucleation time. But it is not quite that, because there is an additional factor here. And this is actually the big factor, because this is precisely the exponential suppression. So it is a factor of order 10 in our simulations. And here is the energy of the critical bubble. So in this simple toy model, when we have just one field and one coupling, this is simply the energy of the critical bubble. But in more general case, when we have a theory of many species and many couplings, this really has to be the energy computed in the effective potential. So this is the effective free energy of the critical bubble. So several comments about this condition. First, okay, our numerical results are consistent with this condition. But of course, we keep checking it, doing more simulations in a different theory. Second, the analog of this condition is actually long known in physical chemistry, where people study systems of one or several degrees of freedom coupled to the Higgs boson, modeling the dynamics of various reaction rates. This condition is written in a different way here. Instead of the thermalization time, one should use the inverse damping coefficient. But this agrees with our condition, because in the Langevin simulations, we see that the damping coefficient is precisely the inverse thermalization time. So next important comment is that now we must understand whether or not this condition can actually be satisfied in a given theory. And one can immediately notice that no, in fact, it is unavoidably violated, at least in weakly coupled theories with just one coupling or one field. And this is what we see in this example. But this is not even about the number of dimensions. So we see that in 1 + 1 dimension, the condition is always violated. But also in 3 + 1 dimension, it is violated as well. And the reason is very simple. Here, the thermalization time is proportional to inverse power of the temperature. So if you want the condition to be satisfied, you need to take the temperature big enough. And then it happens that in such a regime, the theory is not at weak coupling anymore. So you take the big enough temperature, the theory becomes strongly coupled. And in our case, that means that decays are not exponentially suppressed anymore. So we are just we are not in the semi-classical approximation anymore. And in theories with many species and many couplings, the condition must be examined on a case-by-case basis. But results like the analysis shows that it is actually not quite easy to satisfy this condition, even in theories with many degrees of freedom. And the fundamental reason for that is, of course, when you introduce additional degrees of freedom, the thermalization time reduces, right? Because now the size of your Higgs boson, or the coupling of the Higgs boson to the relevant subsystem, becomes stronger. But at the same time, those additional fields, they tend to renormalize the free energy. They tend to change the potential barrier, right? And they can, in fact, increase the potential barrier. So they will contribute to this energy of the critical bubble. And so there are different effects. And it is not clear which one wins in a particular case. So this must be tested. Okay, I guess I have no time to talk about
Yeah,
yet
Andrei, just to
another.
say, we have 2 minutes left.
Yes, yes. Okay, I will skip this part because this is a sort of this is not decay rate, but this is about real-time dynamics, the measure about so-called precursors to the critical bubble. So I can, if you about this, we can discuss this a bit more. I come to my conclusions. Um, so clearly, we must have a theoretical. So far, we do these numerical simulations, and we see some disagreement with Euclidean theory. And okay, but then maybe the most important question is, do we really have the theoretical prediction, right? Do we have the derivation which is not based on the Euclidean theory, which is based on a more first principle calculation, right? We must have such a derivation because apparently we cannot perform such numerical simulations every time we want to measure the decay rate. And that is one important question that you have to answer. Yeah, this is work in progress, which also includes, so such a derivation would also include the derivation of this thermalization condition, right? Because such derivation must also show when we recover the Euclidean theory. The next important question is if this thermalization condition, assuming that this conjecture is actually true, whether or not this condition satisfied in real-life systems featuring first-order phase transitions. For example, is this condition satisfied in standard model thermal plasma in the early universe, or in various extensions of the standard model when you have a first-order electric phase transition, for example? This is not obvious. Is this condition satisfied in, for example, in liquid droplet nucleation in supersaturated vapors? That's what they measure in soft connect. That is also not obvious. The next important thing is, yes, how important are these results for cosmology, for example? Because, yes, the decay rate is different. And if we need an accurate prediction for the decay rate, or if we need to study effects, which is about dynamics of the bubble nucleation, then these results are clearly important. So they might be relevant for other non-perturbative processes not directly related to vacuum decay, such as Sphaleron transitions or production of collision of solitons, because they really tell us that there is some non-equilibrium dynamics. If thermalization is not efficient enough, there is some non-equilibrium dynamics in all these processes, and it might be important. So it's certainly worth looking into these other processes. And at least the question is really go and measure this deviation from thermality and test this thermalization condition in experiment. And okay, let me stop here. Thank you very much.
Thank you very much.